Okay, let's unpack this. We have a massive challenge today. Not just building an electric race car, but engineering a world-class competitive powertrain from the ground up.
Right.
We're looking at an incredibly detailed engineering requirement specification, SOR 15.0, developed by a senior powertrain architect specifically for a newly formed Formula Student Electric team.
That's absolutely right. And this isn't, just some dry engineering document we're flipping through. We're walking through a high-stakes strategic blueprint.
A blueprint.
Yeah, think of it as the McKinsey guide to winning in Formula Student Electric. The core challenge here, the thing that SR 15.0 is all about, is mastering system integration and verification.
Ah, so it's not about the individual parts.
Not at all. It's the difference between having a collection of great components, a powerful motor, a high C-rate battery, and having a functioning, reliable, winning vehicle that actually survives the most brutal event, the 22-kilometer endurance race.
I really appreciate that framing because it immediately tells you where the hard problems are. They aren't in just maximizing component specs.
No.
They're in managing complexity and risk. So before we dive into the spec itself, let's set the strategic context. How has the Formula Student Electric landscape changed to force this kind of thinking?
Well, the competitive landscape has fundamentally moved past what we call the brute force aesthetic.
The brute force aesthetic.
Yeah, the era where you could just bolt on the biggest motor you could find and win.
Oh,
That's long gone. The rules, particularly in top European series like FSG, they impose a hard limit.
The 80 kilowatt cap.
Exactly. An 80 kilowatt continuous power output. And that power cap has shifted the competitive edge entirely away from simple horsepower and, toward finesse.
So if every team is capped at 80 kilowatts, where? Where do you find the margin for improvement? Where's the performance gain hidden?
It's hidden in three critical strategic areas. The source material calls them the key value levers, and they come from extensive sensitivity and failure mode and effects analysis, or FMEA.
Oh.
First and foremost, reliability over peak performance. This is the core survival strategy.
That sounds completely counterintuitive for racing. Why would you prioritize reliability above, say, a faster acceleration time?
It all comes down to the point structure.
Yeah.
The endurance event alone is worth 250 points.
A huge chunk.
A huge chunk. And that score is deeply coupled with the efficiency score, which is another 75 to 100 points. Now, if you do not finish a DNF, you instantly score 0.
0 for both of those.
0 in those 350-plus point categories. And the data shows that over 40% of electric teams DNF.
Wow.
And it's usually because of poorly integrated thermal management, low-voltage cutoff triggers, or, and this is the crucial one, software control logic errors. A DNF instantly drops a team out of the top 50 globally. So reliability is the guaranteed pass to those core 350 points.
So it's the difference between aiming for one fast lap and aiming for strategic survival. I can see why that's lever one. What's the second lever that unlocks performance when power is capped?
It's software-defined dynamics. Since the electrical power is a known maximum 80 kilowatt, the marginal performance gain comes from how efficiently and precisely you use that power to manage the tire's grip.
Right.
This mandates a shift to sophisticated real-time control. We're talking specifically about using the advantages of a four-wheel drive architecture, not just for straight-line traction, but for precise torque vectoring TV.
And what kind of algorithms do you need to make torque vectoring truly competitive?
You need advanced stuff. You need algorithms like Model Predictive Control, or MPC.
Okay.
This control strategy allows the vehicle to run right at the physical limit of the tire's friction circle. That's the maximum grip envelope. By rapidly and independently adjusting the torque to each wheel, the software can generate a precise external moment, a twist, on the car.
So you're effectively using code to create additional cornering speed.
That's exactly it. You're creating cornering speed that brute power alone just cannot achieve. It's truly manipulating physics through code.
That's where the engineering finesse really shines. So what's the third strategic value lever?
Efficiency-driven design. Now, you might think efficiency is just about using less energy, but the FSG efficiency score is a ratio. It's your energy consumption relative to your finish time.
Ah, so you get penalized if you're too slow, even if you sip energy.
Precisely. To max out this score, the entire powertrain must be designed to operate in its highest efficiency island. We're talking greater than 95% for at least 80% of the whole endurance drive cycle.
And that demands two things, I imagine.
It does. First, motors and inverters with high partial load efficiency, and second, critically, a highly optimized regenerative braking strategy.
So the mission is clear. We have to cross this valley of death from being a pile of powerful components to realizing whole vehicle performance.
That's the goal.
And we're starting at the foundational layer, subsystem interface requirements, SRR 15.1.
Exactly. We begin with the integration philosophy because the greatest risk, especially for new teams, is the failure of highly coupled systems. Failures cascade so rapidly from poorly defined boundaries.
What's a good example of that?
Well, the source material gives some concrete and frankly terrifying examples. The high-frequency electromagnetic interference EMI, generated by the inverter couples into and corrupts the low-voltage CAN bus communication lines, causing the car to just fault out.
Right.
Or a less obvious one, thermal expansion mismatch. It leads to stress and eventual leaks in the high-voltage compartment seals.
So the goal is to define every boundary, every handshake between components, right down to the physical fasteners and the seals.
Every single one.
Let's dive into the high-voltage tractive system first. I see some strategic advice here on voltage architecture. 400 V to 550 V nominal, even though the rule max is 600 VDC. Why stick to that specific band?
It's a critical trade-off. It's about balancing electrical performance, weight, and component longevity. If you go too low, say below 400 V or even 300 V to get your 80 kilowatt peak power, Ohm's law dictates that your current IPV becomes massive.
And massive current means massive problem.
Exactly. High current requires thicker, heavier wiring harnesses all through the car.
Ugh.
Plus, heat generation is proportional to the square of the current I2R dollars.
Ah, the square.
So very high current severely increases heat losses, which means you need larger, heavier cooling systems. On the other hand, if you push right up to 600 V, you risk operating near the physical tolerance limits of your standard power electronics capacitors, MOSFETs, IGBTs.
And pushing those limits increases the chance of failure.
Significantly. You risk catastrophic reliability failure. So that 400 V to 550 V range is strategically chosen to optimize wire weight, current flow, and most importantly, component reliability and margin.
That is valuable, practical advice that saves both weight and a lot of headaches. Now, let's talk accumulator safety specifically, a crucial safety detail in the source about the BMS and the FSG 2026 rule update on thermal monitoring.
This is a huge point of failure in scrutineering. The rule changed specifically because teams were doing what scrutineers call ambient air measurement.
So they were just measuring the air in the box.
Or measuring the temperature of a thick copper busbar data, which is almost useless in the event of a cell-level failure. The new rule is extremely stringent. Temperature sensors must have direct thermal contact with the cell body itself.
Okay.
And they have to be positioned within 10 millimeters of the negative terminal, which is statistically the hottest point during a high current discharge.
So this is now a mechanical and a packaging requirement that dictates how the entire battery module has to be assembled. It affects your insulation, your complexity.
Precisely. And the requirement doesn't stop there. The design must support direct monitoring of at least 30% of the total cells in the pack.
Wow.
And if your BMS can't continuously broadcast this critical data, specifically the max cell temp and min cell voltage, via an isolated CAN bus at 10 Hz or more, your VCU can't do its power derating calculations.
And you fail safety checks or you DNF in endurance.
Exactly. The VCU needs that high-frequency data to make immediate protective decisions.
Speaking of capacity, the strategic advice suggests 6.0 to 7.5 kilowatts. Why that specific window?
That range just ensures a sufficient energy margin. You need enough for the 22 kilometers of endurance, plus an extra margin for warm-up, driver errors, and critically for the efficiency test itself.
Right.
If you size the pack too small, even minimal losses or unexpected drag will trigger a low-voltage cutoff, DNF. That capacity is your safety net.
Let's transition to the inverter and motor integration. This section, SOR 15.1, is emphatic that electromagnetic compatibility EMC is king.
Well, because the inverter is a source of chaos. It uses high-speed switching of immense currents, often thousands of times per second, to generate the motor phases. This whole process just generates massive amounts of high-frequency electrical noise, or EMI.
And if that noise gets into your low-voltage sensor lines?
Which are usually right next to the high-power cables.
Right.
It corrupts the data.
Give me a vivid example of that corruption. What happens on the track?
The VCU suddenly loses communication with the inverter. Or worse, the motor's resolver sensor, which tracks the rotor position, it picks up the noise.
So the VCU gets garbage data.
It might suddenly think the motor is spinning at 15,000 RPM when it's stationary. Or the angle is just shifting erratically. That false chaotic data instantly throws the control logic into disarray and forces a catastrophic safety shutdown. The car just stops.
So how do we stop this invisible high-frequency enemy?
You have to use high-quality, shielded cables for the three-phase HV connection. But the crucial integration requirement that gets overlooked all the time is the 360-degree termination grounding of that shielding.
So it's not enough to just ground it with a little wire?
You cannot just ground the shield using a pigtail wire at one end. High-frequency noise flows only on the outside of the shield. If that shield isn't connected all the way around 360 degrees to the chassis ground at both the inverter and the motor ends, the noise just jumps right off the shield and into your sensitive sensor wires nearby.
That means teams need specialized EMC cable glands that physically clamp the shielding braid to the metal housing of the component itself.
Yes,
So it's a mechanical precision requirement for electrical reliability.
it is absolutely non-negotiable. It is the only effective way to shunt that high-frequency noise to ground before it can corrupt low-voltage signals like the resolver or the CAN bus.
Moving to the nerve center, the low voltage control and safety systems. To run the sophisticated MPC algorithms we've discussed, what exactly does a world-class VCU require in terms of hardware?
It needs serious, real-time computational muscle, not a hobbyist Arduino.
Right.
We are talking about a real-time microcontroller, like an STM32H7 or a TIC2000, running north of 200 MHz. And crucially, it requires a dedicated floating point unit, an FPU.
Why is that FPU so essential?
The FPU is the hardware accelerator for handling complex math with decimals. Torque vectoring and MPC rely on constant lightning-fast calculations of trig functions, matrix inversions, all these operations using non-integers.
And if you try to do that in software?
The delay is just unacceptable for the microsecond-level precision you need for real-time dynamic control. The FPU ensures the VCU can crunch the numbers fast enough to keep up with the car.
And the VCU's I/O, its inputs and outputs, are equally dictated by the safety rules.
You absolutely are. Safety, demand, redundancy. The VCU requires two independent APPS accelerator pedal position sensors.
Okay.
And critically, these two sensors must have different transfer functions, say one linear, one exponential. This is Rule T 11.8 for the plausibility check.
And what does that check do?
If the VCU sees the two different functions deviating by more than 10%, it knows one sensor has failed, and it must immediately cut torque to zero. This prevents a failure where both sensors get stuck at 50% and confuse the VCU.
And for communication.
At least two independent CAN bus channels. You need a high priority channel just for critical powertrain, data, BMS faults, IMD status, VCU torque commands.
And the other one?
A separate lower priority channel for non-critical logging, telemetry, debugging. Segregating the data prevents low priority logging traffic from potentially delaying a critical safety message.
Let's discuss the ultimate authority, the shutdown circuit. This is where the control logic ends and hardwired safety begins.
And the source insists this must be a purely hardware serial loop. The VCU can monitor the nodes on this loop, the E-stops, the inertia switch, the IMD fault, the BSPD fault. But the VCU is only a witness.
Only a witness.
The physical loop connects all these safety nodes in series, and that loop controls the final coil power of the errors, the accumulator isolation relays.
So, if the inertia switch detects a major crash, the hardware loop physically opens the relay, regardless of what the VCU software is doing.
Exactly. Or even if the VCU itself has failed. The software can trigger a shutdown, but it can never bypass or control that final error's coil power. That immediate hardware-mandated power cut is the final fail-safe and a non-negotiable scrutineering requirement.
Finally, for this section, the thermal and mechanical interfaces. You strongly advocate for a dual-loop cooling strategy. Why invest in the complexity of two separate systems?
Because their thermal requirements are fundamentally incompatible. Loop A, for the motor and inverter, can tolerate and even function efficiently at high temperatures, say 60 to 80 degrees Celsius.
Yeah.
But Loop B, for the battery accumulator, needs extremely low uniform temperatures, ideally below 55 degrees C, to maximize battery life and performance consistency.
And what's the consequence of sharing a single loop?
The motor, which is the biggest heat generator, will raise the temperature of the shared coolant. That hot coolant then risks flowing back toward the battery, raising its core temperature,
Which leads to
premature thermal disrating. The battery hits its temperature limit faster, forcing the VCU to cut power, which costs you critical time and points in endurance. The dual loop is a strategic investment in maintaining independent thermal control to maximize usable power for the whole race.
And one final constraint tying mechanics to software. We noted that to implement advanced control like torque vectoring, the car has to use dual motor rear-wheel drive or 4 in-hub motors. A single motor just can't do it.
That's the key linkage. The software goal drives the mechanical architecture. If you want to generate that dynamic yaw moment that helps the car rotate, you have to have the mechanical ability to apply asymmetrical torque, pushing one side and pulling the other.
Which a single motor with a differential can't do.
Not at the level of control required for world-class TV, no.
This brings us perfectly to part 2, the System Integration Strategy, SOR 15.2. This section demands the use of the V model and mandatory hardware in the loop, HIL verification.
It does.
The source calls the most fatal mistake for new teams first-time testing of control software on the completed car. Why is that so disastrous?
It's the trial and error method, and it is just inefficient, unsafe, and extremely risky. Every time you test unverified code on the physical vehicle, you risk frying extremely expensive components.
A $20,000 inverter, for instance.
Or an entire accumulator pack. The V model establishes a rigorous scientific validation roadmap that moves development from the abstract idea to the physical reality in managed, verified steps.
Let's break down that layered verification pyramid of the V model. It starts with the theoretical, right?
It starts with the abstract idea, that's MIL, model in the loop. You're testing your core algorithms, your MPC logic, your BMS calculations in a purely mathematical simulation, usually a MATLAB Simulink.
Just to see if the math works.
Exactly. Does the mathematical concept achieve the desired performance? That's all you're asking.
Once the math is proven, you step down to SIL, software in the loop.
Correct. Here you take those high-level algorithms and you automatically generate C code from them. SIL is where you test that generated code for numerical precision errors, resource consumption, compilation mistakes, before that code ever touches the actual VCU hardware.
This is all still virtual, but HIL is the essential pivot. It brings the hardware into the loop.
HIL, hardware in the loop, is the mandatory bridge. You stop simulating the controller, you use the actual VCU hardware, the unit under test, or UUT running this final flight firmware.
But instead of a real motor, it's talking to a simulator.
It's talking to a high-speed, real-time simulator, often called the plant. This verifies the VCU's physical interface, its I/O drivers, its ability to handle CAN latency, and its ability to execute its tasks within hard real-time constraints.
And finally, when HIL is complete, you move to VIL, vehicle in the loop, which is the final calibration on a dyno or the track.
And that systematic approach saves your time and protects your hardware.
Now let's talk practically about the HIL setup for a university team. Commercial HIL platforms like DSpace they're prohibitively expensive.
They are. So the architect's solution is a highly pragmatic, high-value, student-grade solution.
What does that solution look like?
You still use the flight VCU PCB as your UUT, but the real-time simulator, the plant, is replaced by an affordable, high-performance development board, something like an STM32H7 or a TIC2000 Launchpad.
So this low-cost board is programmed to run the digital twin model of the car?
And mimic every single component interface.
So this little board simulates being the motor, the battery, the brake pedal, and all the wheel speed sensors at the same time. How does it physically communicate with the VCU?
It uses its outputs to generate signals. It uses digital to analog converters, DACs, to generate voltage signals that mimic pressure sensors or the EPPS signal. It uses PWM outputs to generate realistic wheel speed pulses, and it uses its CAN module to rapidly reply to the VCU's requests for BMS or inverter status data.
That's clever. The VCU literally cannot tell the difference between talking to a real car and talking to the simulator board.
Exactly.
But you mentioned a critical piece of custom hardware is still required, the signal interface board.
This custom PCB is essential. The VCU and the simulator usually operate at different voltage levels. The interface board handles necessary tasks, like level shifting, taking the simulator's 3.3V DAT output and boosting it precisely to the 0.5V or 0.10 range the VCU expects. It's the handshake translation layer.
And here's the most crucial part for rigorous verification, the fault injection relays.
Yes. Most teams only test for software bugs. World-class verification tests for catastrophic real-world failure. The fault injection relays are physical devices on the interface board used to intentionally and automatically break, short, or introduce impedance into physical connections.
Why physically inject the fault? Why not just simulate it in software?
Because a software simulation can't truly replicate a physical wire breaking. You need to verify that when a sensor wire is severed, the VCU detects the resulting signal loss and immediately executes the correct, safe, fault handling logic.
Like shutting down the inverter or defaulting to a safe torque limit?
Exactly. The HIL must be able to test the VCU's resilience to unexpected disconnection. a common failure mode on a race car due to vibration.
To make this system work, the simulator needs a highly accurate brain, the digital twin of the car. What are the key fidelity requirements for this plant model?
It must be challenging enough to stress the VCU. Minimally, the model needs to be a 7-degree of freedom model to accurately simulate core vehicle dynamics, longitudinal, lateral, yaw, and the 4 independent wheel rotations. If the model is too simple, the VCU's control algorithms will work in the lab but fail instantly on track.
And the powertrain models themselves. They're simplified but strategically accurate. Tell us about the battery model.
For the battery, we use a simplified Thevenin model, often a second-order RC equivalent. We're not simulating chemistry, we're simulating electrical response. This model accurately reflects the voltage drop, the FAG based on internal resistance and current draw.
And that's critical for testing.
For verifying the VCU's protection logic, we need to verify that it correctly limits power when the simulated current draw causes the VSL threshold to be approached. It's testing for voltage brownouts, which are instantaneous triggers for safety shutdowns.
And for the motor model?
We use a simplified first-order torque response model. The key here is simulating the inherent latency between when the VCU issues a torque command and when the motor actually delivers that torque.
Right.
The VCU's MPC algorithm has to account for this latency. If it doesn't, the car will oscillate or overshoot its control targets.
And finally, the requirement to overlay Gaussian white noise. That sounds like you're intentionally trying to sabotage your own testing.
You are. You're simulating the electromagnetic interference that will inevitably happen in the real car. The VCU must run filtering algorithms to clean up noisy inputs.
I see.
If the filters are too weak, the noise corrupts the data. If they're too aggressive, they introduce too much delay. You have to verify that your filters are robust enough to handle the simulated noise without introducing unacceptable latency.
This rigorous setup culminates in the final non-negotiable step in SRR 15.2, automated regression tests. These have to run successfully after every single firmware update. Let's detail the 3 mandatory test procedures, starting with the APPS.
TP 15.2a verifies APPS plausibility. The HIL rig is programmed to simulate the 2 independent APPS voltages diverging by more than 10%. This divergence signifies a failure. The hard requirement is that the VCU must detect this error and cut motor torque to 0 within 100 milliseconds.
100 milliseconds.
And automated testing ensures this time limit is met every single time.
TP 15.2b covers the BSPD, the brake system plausibility device.
This test simulates simultaneous driver error, brake pressure above 30 bar, and the accelerator open above 25%, or making over 5 kilowatts of power. It's a contradictory state. If the VCU detects this, it must instantly cut power.
And the HL rig just runs that scenario over and over.
Verifies the logic paths under that critical safety failure condition.
Yes, and the final HIL test, TP 15.2c, is the ultimate dry run for the main event.
This is the endurance thermal simulation. The HIL rig inputs the entire 22-kilometer race velocity profile into the digital twin. The VCU is monitored. The test verifies that when the simulated battery temperature exceeds the critical safety threshold, say 55 degrees C, the VCU correctly triggers its torque derating strategy.
And
Crucially, the test must confirm that this transition is safe and that the system doesn't crash or exhibit any unstable behavior while cutting power. Passing these 3 automated tests mitigates, I'd say, 90% of the common system failures that plague FSE teams.
That is an exhaustive scientific strategy for shifting development from the track into the lab. Now we move to part 3, SOR 15.3, where pure performance is defined. Dynamic tuning and model predictive control, MPC. We need to explore why simple, reactive PID controllers or basic lookup tables fail at the nonlinear extremes of race car handling.
Traditional PID controllers are fundamentally reactive.
Yeah.
They only look at the error right now, say the car is understeering, and they try to fix it. They have no concept of future constraints or consequences.
Right.
Race car dynamics at the limit of grip are highly nonlinear, unpredictable, and subject to instantaneous constraints, like the max current the inverter can supply. A reactive controller just cannot handle that complexity.
Whereas MPC is predictive and global.
Exactly. MPC is an optimal control strategy. It uses that digital twin, the dynamic bicycle model, to predict the vehicle's future state over a prediction horizon.
So it's looking ahead in time.
A few steps, yes. It then uses a quadratic programming solver to solve a complex optimization problem in real time 20 to 50 times per second to find the sequence of torque commands that minimizes a predefined cost function while respecting every physical constraint.
And that's how you get active trajectory tracking and maximum grip utilization.
That's how you do it.
Since the solver is predicting the future, we need to understand the mathematical model it uses. It focuses on two key state vectors, lateral velocity and yaw rate.
Right, and the control input is CMC, the extra yaw moment from torque vectoring. The model defines how the lateral forces from the tires and that control input influence those states. Now, for microcontroller speed, the complex physics are often simplified. We use a linear approximation, alpha, for the immediate future.
To keep it solvable in milliseconds.
Exactly. But the true engineering artistry lives inside that cost function, $.
Okay, let's talk about that cost function. It's where the team embeds its strategic trade-offs, performance versus efficiency versus durability. It has three main components defined by the weight matrices, $2 and $. Let's start with the $2.
The $Q matrix defines tracking performance. It assigns a penalty to the error between the car's actual state and its desired reference state, the optimal racing line and speed.
Okay, give me an example.
Let's say your car is understeering badly in a tight hairpin. This means your actual yaw rate is lower than the reference yaw rate. So if you want the controller to eliminate that understeer aggressively, what do?
You'd want to penalize that error more heavily.
Exactly. You significantly increase the weight. You are telling the optimizer, eliminating yaw rate error is paramount. Pay whatever energy or torque penalty is required to achieve the desired rotation.
So it forces a very strong torque vectoring intervention.
A very strong positive yaw moment, making the car rotate aggressively into the corner. High color means high performance, high accuracy.
So if Twirler is about performance, the Twirl matrix must be the counterbalance.
It is the strategic cost counterbalance. Torque is the control effort matrix. It penalizes the magnitude of the control inputs, the torque commands themselves.
And if you set R too low.
The optimizer sees torque vectoring as free and will use maximum possible current for even tiny dynamic gains. The consequence of that: immediate thermal trouble.
Motors overheat.
The motors hit their thermal limit after just 3 seconds of aggressive use. Your total power is suddenly crippled. By increasing $12, you make torque expensive in the optimizer's calculation. This forces a softer, more energy-efficient strategy.
So you're trading a tiny bit of peak cornering speed for durability and efficiency points.
It's the strategic tension at the heart of FSAE.
And finally, the subtle but mechanically vital lower delta matrix, the slew rate.
This is the durability matrix. It doesn't penalize the amount of torque, but the rate of change of that torque. If the torque commands change too rapidly, say from 5 nanometers to 100 meters in 1 millisecond, it introduces severe shock loads into the gearbox, the CV joints, the entire drivetrain.
And this shows up on track as vibration or chattering.
Exactly, as the controller rapidly switches between positive and negative commands.
Yeah.
So to eliminate that harsh chattering, you would increase Groll delta. It smooths the control output, forces the torque commands to ramp up and down gradually. It's like adding damping.
So the art is finding the perfect balance between aggressive tracking, high Q, energy saving, high R, and physical durability.
That's the tuning process in a nutshell.
This entire system, though, relies entirely on the quality of that prediction model. As the architect notes, garbage in, garbage out.
Yes.
You need high-quality telemetry to accurately identify those model parameters, especially tire cornering stiffness and yaw inertia, TLE.
That's where the data acquisition strategy comes in. The VCU or a lidar must record raw data steering angle, yaw rate, lateral acceleration, vehicle speed at a sampling rate of at least 100 hertz. You need that rate to capture the rapid transients.
How do teams use this raw track data to estimate something as complex as tire cornering stiffness, Kalfa?
They run specific tests, like the skid pad and slalom. We use kinematic equations, usually from the single-track model, to calculate the front and rear slip angles.
The slip angle, the difference between where the tire is pointing and where it's actually going, that sounds tough to calculate because it requires knowing the lateral velocity, 5 yaw.
It is notoriously difficult.
Yeah.
Lateral velocity is rarely measured directly on student cars. High-level teams use sophisticated techniques like Kalman filtering, or they just integrate the lateral acceleration.
I see.
Once you have the slip angles and the lateral force, you plot force versus angle.
And Kalfazella is simply the slope of that resulting curve in the linear region.
Exactly. Using linear regression tools, like in Python, you fit the linear region of that data. The slope is your cornering stiffness. Kalfazella, if this value is off by even 10%, your predictive control will be significantly misaligned with reality.
And there's an advanced insight here that truly separates the top teams: the sensitivity of the tire to vertical load.
Absolutely. The small 10-inch FSE Hoosier tires are highly sensitive to vertical load. FSAE. During braking or cornering, mass transfers dramatically. A world-class team knows that Kalfa isn't a fixed number. It's a function of 5NE.
So they build a model of the model.
They build a multi-dimensional lookup table, or a simple neural network, to model Kalfa FCDZ day. When the MPC runs, it calculates the load transfer dynamically and pulls the appropriate Kalfa T for that specific tire at that specific moment. This drastically improves the MPC's predictive accuracy at the limit.
That's leveraging the data to redefine the model itself. Once the model is tuned, we go back to the strategic tuning of Q and R. Let's use the diagnostic table to solve problems. Scenario 1, you have a soft, understeering car, slow turn in.
Diagnosis. The controller undervalues yaw rate error. It's not aggressive enough. The strategy. Increase the yaw rate weight. This makes the optimizer pay more attention to rotation error, leading to a much stronger torque vectoring intervention.
Scenario 2, the car feels fast, but it's unstable. You get oscillation or chattering on straightaways.
Classic high-gain problem. Diagnosis. The controller's too aggressive, generating rapid, high-frequency torque changes. The strategy. Increase on delta. The slew rate weight. This introduces a necessary smoothing or damping to the control output.
Scenario 3, lap times are great, but the motors are overheating or consumption is too high.
Diagnosis. The system is paying too much energy for marginal dynamic gains. The strategy. Increase $3 the control effort weight. By making torque vectoring expensive in the optimization, the solver defaults to a more conservative, energy-efficient approach.
Before we move on, we have to touch on the cutting-edge dynamic adaptation using Gaussian process GP learning. This is tuning the car while it races.
This is the frontier. GP learning is a non-parametric approach to online model adaptation. The MPC predicts the car's state based on its static model, but the IMU, the inertial measurement unit, measures reality.
And if there's a discrepancy?
A model residual. The GP learning module introduces a real-time correction term to the model. It's learning, for instance, that the rear tire grip is diminishing due to rising temperature, or the track is dirty in a specific section.
This ability to learn while racing compensates for factors like tire wear and temperature changes, allowing the control system to maintain maximum grip constantly.
It shifts the entire paradigm from static calibration to dynamic resilience.
That powerful dynamic capability transitions us to part 4, the acid test of system integration endurance and thermal management, SOR 15.4. This is the ultimate crucible.
This is where reliability wins the day. The 22-kilometer endurance race is designed to expose every single weakness. The system must operate long enough to reach and maintain thermal equilibrium.
Not like the 4-second acceleration event.
No, endurance demands sustained high power. If your cooling system is inadequate, the car will fail spectacularly, likely around the 15 to 18-kilometer mark.
The strategy requires rigorous simulation before assembly. Let's start with the drive cycle simulation. How do you define the load?
Teams use real or synthetic track models, like data from FSG Hockenheim, to generate the theoretical fastest possible velocity curve. This curve is based on the vehicle's GG diagram. This curve is your demand profile.
You then use that velocity demand to calculate the power spectrum. You stress that the critical metric here is RMS current, not average current. Why?
Because heat generation is governed by the square of the current, tiny to LR dollars. Average current smooths out the peaks and troughs, giving you a falsely optimistic picture. The root mean square, RMS current, accurately represents the heating effect.
Okay.
For FSE endurance, a pack monitor REMs between 80A and 120A is typical, and the cooling system must be designed to continuously manage the heat generated by that RMS value.
This feeds directly into the thermal network model.
This is a complex simulation, typically built in software like MATLAB Simscape. You have to model every heat source, the internal resistance losses in the battery, and critically, the conduction and switching losses in the inverter and motor.
And on the rejection side,
you need detailed modeling of the heat rejection. The radiator model, dependent on coolant flow rate, and crucially, the air convection coefficient, which must be modeled as a function of vehicle speed, $5. If you assume constant airflow, you'll grossly underestimate the heat buildup in slow speed sections.
the simulation success is tied to 3 extremely specific KPIs. What is the critical temperature limit for the battery?
KPI 1, battery temperature. In a 30 degrees C ambient environment, the battery core temperature must remain strictly below 58 degrees C. This leaves a critical 2 degrees C safety margin. If the model predicts 61 degree, you fail the design.
KPR2 focuses on the cost of managing the heat. derating time.
Torque limiting due to overheating, whether it's the motor, inverter, or battery, must not exceed 5% of the total race time. If the VCU spends more than 5% of the race cutting power, your cooling package is fundamentally flawed.
And KPI 3, energy budget.
For a typical 7 kilowatt per pack, the total simulated consumption must be less than 6.5 kilowatt buffer. This 0.5 kilowatt buffer ensures a margin against BMS's low voltage cutoff. Hitting this target guarantees completion.
Let's talk about the efficiency points grab, regenerative braking. Since recovered energy is fully credited, this is huge.
It's the easiest place to find energy. The strategy involves precisely mapping the regen torque to the brake, pedal-brake blending, or optimizing it for throttle liftoff. But regen introduces significant risks.
What are those critical verification points?
First, dynamic stability. You have to verify that regen torque doesn't cause rear-wheel lockup, especially during turn-in. Second, battery health. The regenerative current must never exceed the battery's maximum charge current limit, CCL. Overcharging, even for a moment, severely damages the cells.
And if the simulation predicts you'll hit the energy budget limit, you need a proactive energy management strategy, EMS.
The EMS is the strategic safety net in the VCU. It operates predictively. If the state of charge falls below a predefined target curve for the remaining distance, the VCU implements a hard energy limiter, globally restricting max power to, say, 90%. And this has to be HIL verified.
After all this modeling, the final verification is the full-flow simulated endurance on the track.
This is the full dress rehearsal. 2 11-kilometer stints with a driver change. The key here is not just completing it, but data validation. Teams must compare the measured temperature curves from the track against the model's prediction.
And if the error is too big?
If the error is greater than 5 degrees C, it means the thermal resistance parameters in the model are wrong, or there's a major physical flaw, like air pockets in the cooling system, which must be diagnosed and fixed.
We have meticulously defined the requirements for design, integration, software validation, and thermal durability. Now, for the final piece, SOR 15.5, compliance and scrutineering. The reality is you can build the fastest car in the world, but if it doesn't pass tech inspection, it's useless.
Absolutely. Scrutineering is the mandatory quality gate, the ultimate verification. The grim statistic is that 20 to 30% of new teams die in the garage by failing inspection. The entire design strategy has to view every compliance check as a fundamental design constraint.
Let's review the key EV2 electrical checkpoints that cause failure. The insulation monitoring device, IMD test.
The rule mandates the IMD must cut the ARs within 30 seconds when insulation impedance drops below the standard 500 AV threshold, about 250 kV for a 500 V system. The practical advice is to build a variable resistor box and test this threshold weekly in the lab. If you can't prove your IMD triggers the shutdown, you fail.
Next is the TSAL, Tractive System Active Light.
The critical point here is that the high voltage measurement driving the TSAL logic must be hardware implemented and completely independent of the VCU software. The rule demands above 60 V flashing red, below 60 V with LV on constant green.
This ensures that even if the VCU fails, the car is still externally verifiable as safe or unsafe.
Exactly.
And the simple but frequently missed interlock loop.
It's the simplest yet most catastrophic failure point if missed. If you break any HV connector motor, inverter battery, that interlock loop must instantaneously trip the airs. It has to be a physical, immediate interruption of power.
Beyond electrical, we have the environmental and mechanical checks, notably the rain test.
The rain test is a severe test of your sealing strategy. The car must withstand 2 minutes of water spray without the IMD reporting a fault. This requires all HV connectors to be robustly IP67 rated. But there's a subtle detail about the accumulator box that gets missed.
What's that?
You need Gore-Tex vents.
Gore-Tex vents on the battery box. Isn't that inviting moisture?
Quite the opposite. They're vital for pressure equalization. If the battery box heats up and then cools rapidly, a vacuum can form inside the sealed box. That vacuum literally sucks moisture through microscopic gaps and seals. The Gore-Tex vents allow air pressure to equalize while blocking liquid water, preventing this failure mode.
Finally, the brake test. All 4 wheels must lock simultaneously. Why is this specifically challenging for EVs?
It's purely mass distribution. The heavy accumulator pack significantly shifts the center of gravity rearward. If the team calculates the hydraulic brake bias using traditional methods, they'll often find the front wheels lock up early, but the rears won't. Precise brake bias calculation, accounting for that rearward cog shift, is absolutely mandatory to pass.
This brings us to the conclusion and the implementation roadmap. We've covered integration, validation, dynamics. What is the core strategic advice for year 1?
The core advice is intensely pragmatic and must be delivered brutally early. The first-year goal is completion, or one sai, as we say in the Asian series.
Completion.
Do not waste precious resources chasing lightweight design, complex aero, or exotic materials. Focus 100% of your energy and time on reliability and integration verification.
If resources are limited, where should the team make the priority investment that guarantees the best return on points?
Prioritize the HIL test platform, SOR 15.2, and thermal management verification, SOR 15.4. If you can rigorously test your control software on HIL and ensure your car won't thermally degrade in the last 5 kilometers of endurance, you are guaranteed to overtake at least 50% of your competitors who will retire.
So we spend a whole year building a complex machine, and the strategic advice is not to chase the fastest motor, but to focus on boring temperature checks and safety logic verification. Isn't that low ambition?
It is the definition of high strategy based on risk management. The points for reliability and efficiency are stable, high-value assets. Speed is highly variable. If you achieve stable, efficient completion, you score 350 plus points, and you place highly.
And if you don't?
If you spend time chasing a 2-second gain in acceleration and fail endurance, you score 0. That strategic decision prioritizing completion is the single most important decision for a first-year team seeking a top 50 global result.
The metric of success isn't blistering lap times, it's stability and passing the efficiency test. Let's map out this development timeline using the McKinsey phases.
Months 1 to 3 is the definition phase. Finalize all 15.1 interfaces and complete the HIL model construction, your digital twin. Months 4 to 6 is the simulation and software testing phase. Rigorous HIL testing of the VCU software and the SimScape thermal model.
Then the build.
Months 7 to 9 is the physical build. Vehicle assembly, running concurrent scrutineering pre-checks like the rain test and insulation monitoring.
So you're building the car concurrently with testing its safety components to catch failures early.
Exactly. Then month 10 is dedicated track testing and raw data acquisition, collecting that crucial telemetry at 100 Hz or more. Finally, month 11 is the data optimization phase, executing the 15.3 parameter identification, calculating alpha low, and performing the final MPC tuning of Q&R based on real track feedback. This structured approach prevents catastrophic last-minute failures.
To synthesize this entire deep dive, the path to a world-class FSE car isn't about finding a component with a slightly higher spec.
Well,
It's about achieving perfect harmony between every line of code and every mechanical and thermal interface at the system level. The true competitive margin is created not during the race, but in the lab, through rigorous upfront verification.
that is the ultimate conclusion. The difference between a winning team and a failing team often boils down to a 5 degrees Celsius thermal margin in the final kilometers of endurance. A margin that can only be created by rigorous HAL verification and accurate thermal modeling executed early in the development cycle.
We've spent considerable time discussing how leading teams are moving beyond that static calibration to dynamic control using Gaussian process learning, where the car essentially learns during the race to adjust its control algorithms based on real-time track data.
Adapting to tire wear, temperature changes.
Right.
That ability to learn while racing is the key. It suggests that the most critical component in future high-performance systems won't be the advanced materials like silicon carbide in the inverter,
But something else.
but the predictive power and adaptability of the VCU's dynamic digital twin. Its ability to understand and react to reality better than a human driver ever could.
Which raises this final provocative thought for you, the listener. We defined a strict strategy for success based on moving from static calibration to dynamic data-driven learning. What parts of your own work or field, whether it's strategic planning, manufacturing processes, or complex system design, could benefit most from transitioning from a static parameter set where you tune once and hope for the best, to a dynamic learning system that adapts in real time to internal changes or external pressures to unlock that next level of performance and resilience? Think about where your own system's digital twin might need to be created and fed with live data.